This chapter proves to be the most difficult for many students just because of the memorization involved. Think of it like trying to learn the alphabet and your times tables and your addition and subtraction all at the same time. Now, not to scare you, we will do lots of practice with this in class. Binary compound, by definition, contains two different atoms, two of them. So this could be like carbon and oxygen, giving us carbon monoxide. It has to have two different atoms to be considered a binary compound, with one exception, but I'll get to that with the polyatomics. Again, two different atoms. Again, what? There's three atoms here, right? Atom 1, atom 2, atom 3, right? But the two different atoms are still present. See, this is carbon dioxide. And even though it has two oxygens and one carbon, they're still just two different atoms. Now let's take a look at this last one. Is this a binary compound? No. This one has three different atoms pictured here. We've got the red ones and the white ones and the black ones. So no, this one is not a binary compound. Binary ionic compounds is where we're going to start. And ionic compounds are made with ions in them. There's two types of ions. We have type 1 and type 2 ions. Now, all ionic compounds are always are going to be made of a cation hooked up with an anion, always. The type 1 refers to metals, the type 1 metals. And type 2 refers to the metals, type 2 metals. The anions, well, they're always the same until we get to the polyatomics. So here's your type 1 metals. You should color those in. And there's your type 2 metals, and you should color those in. What's the difference between these two metals? Well, the type 1 cations, I'm going to go ahead and color it all in again. But the type 1 cations, remember, these are cations. We know the charge, absolutely know it. Everything in column 1 is +1, column 2 is +2. Aluminum, gallium, and indium are +3, zinc is +2, silver is +1. The type 2 cations, we don't know. We don't know the charge. We have to figure it out. We can figure it out. What? We have to figure it out? Yeah, it's not bad. I'll show you how. Binary ionic compound type 1, where we know the charge. We know the charge. It's very easy. Very, very easy. So the first thing you do, let's take a look at this one. The first thing you want to do is name the cation. So that cation, yes, it's sodium. Very easy. Sodium. Oh, I should notice that in an ionic compound, it's always positive, then the negative. It'll always be the cation, then the anion. Because it's better to be positive, that's why the cations go first. Okay, back to where we were, sodium. Now, we simply name the anion, and we change the ending to "ide." So chlorine becomes chloride. These are the easy ones. Because they're so easy. Let's name the cation. So in this case, the cation is potassium. And then we're going to name the anion, changing the ending to "ide." So our anion is sulfur, becoming sulfide. Ionic compound theme, we handled the type 1. We know the charge on these guys. They're known. We don't even have to mess with it. The charges are known. But I said we're going to have to figure these charges out. And that's where it gets a little more difficult. But don't worry, it's not bad. Because if you recall, an ionic compound is a cation. Oh, look, there's a positive cation. And an anion. And the charges have to add up to 0. Absolute rule. And since the charges on the anions don't change and it has to add up to 0, we can figure out the cation. Show you seems to work really well for students. So how do we find the charge on that cation? One of the things that seems to work well is to divide this thing into the cation and the anion. And we know it has to add up to 0. So the charge on the phosphorus, the anion, will never, ever change for an ionic compound. Well, that makes it easy. So the phosphorus has a -3 charge, and we know there's one of them. So 1 times -3 is -3. So what does the iron then have to be? That's right. The iron then has to be a +3 charge. Let's try one a little more difficult. Okay, let's divide this between the cation and the anion. So I'll split it in 2. We know this has to add up to 0, and the charge on chloride is -1. -1 times 2 is -2. Yes, I did multiply those. So what does the charge on nickel have to be? Well, if you said +2, you are correct, because +2 and -2 does add to 0. One more, a little harder. Okay, whew, this one could be brutal. Let's see how we do. All right, I'm going to divide the cation into the anion. Oh, those are nice straight lines. Adds to 0. We know the charge on the anion's not going to change, so oxygen's a -2. And -2 times 3, that's times, is -6. Now, kids want to go, oh, wait, that means chromium has to be a +6, right? No, is not. See, because we need a +6 over here to add to 0. But I happen to have 2 chromiums. So what number times 2 is going to equal 6? Well, if you said +3, you are correct. The charge on chromium is a +3. That one is almost as hard as it gets. Things are a little more complicated with the polyatomics. Don't mean to freak you out, but really that's about as hard as it gets. I want to try FeP. So the first thing we want to do is name the cation. And you know, I should have another rule in here. Let's add another rule because I can. You need to ask, is the cation type 1 or type 2? Well, it's type 2 because, you know, I wrote type 2 up there, but you should add that in the rules. If it's a type 2, you have to find the charge. How are we going to find the charge? Well, that's easy. We're going to cut it in half. Cation, anion. We know it has to equal 0. The charge on phosphorus never changes. I know I did this one on the other slide. So that means it has to be a +3. Now, the new modern way to write these is to put that number in Roman numerals. Yeah, that's the modern way to do it. Really, because we used to have to like change the cation to ferric and ferrous depending on the charge. So instead, the modern way is we're going to use Roman numerals. This 3 represents the charge of the cation. Now, I can't tell you how many times kids see this and they want to make this the subscript. It is not ever, no, never, ever the subscript. It's the charge on the cation. And now it's easy after that. You simply name the anion, changing the ending to "ide" phosphide. And we now have iron 3 phosphide. This one was way too easy, so we should do one more. First, name the cation. Well, this cation is gold. Now, you should ask yourself, is this a type 1 or type 2? Well, yeah, because they said it was type 2 up there. It is type 2, that's true. So we need to find the charge. Well, let's divide this thing into cation and anion. We know it has to equal 0, and oxygen's charge never change. It's a -2. And -2 times 3 is -6. So what does gold have to be? Well, this whole half of the molecule has to be +6. So what number, that's a variable, times 2 is going to equal +6? Okay, good. If you said +3, you got it. The charge on gold is +3. So now simply name the anion, changing the ending to "ide." oxide. Well, a lot of times kids go, wait a minute, can't I just use this number on the anion and it would be true? A lot of times, yes, and not all the time. So be careful with that. If you got nothing else, it's not a bad guess. Charge has to appear in the name and put it in Roman numerals. Now, the question I always get asked is why? Well, let me explain why. This is iron 2 oxide. Now, let's see. We divide that in half. We know it equals 0. Oxygen's charge is -2. That means iron has to be +2. Iron 2 oxide. Okay, so let me show you what iron 2 oxide looks like. It's this black pigment that's used in mascaras and tattoos. But if we oh, that's a funky place to put it. Well, oh well. We'll run with it. It has to equal 0. Oxygen's always -2 times 3 is -6. This side has to be +6. So what number times 2 makes +6 plus 3? So this one is iron 3 oxide. Look at what this guy is. Da-da-da-da, this one's rust. It's used in shoe polish and manufacturing and optics. It's all kinds of things. They're very different. We certainly wouldn't want to mix this up if we were in a tattoo parlor, would we? Ooh, that would be bad. That's why we need to know the charge in the name. Don't forget, this is the charge, not ever the subscript. Up next, we're going to tackle type 3 binary compounds.